Bismillahirrahmanirrahim. The finite element method allows us to solve stress analysis problems that we cannot solve analytically. Take this problem as an example. This irregular shaped plate of some thickness, it is subjected to a force here and is attached to a rigid frame here. Now, its analytical solution would amount to a distribution of stresses or displacements that satisfies the differential equations uh, throughout this region, throughout the whole plate, as well as the solution must yield boundary conditions here. Now, for this problem, that is not possible, as is the case with most other problems, unless they are exceedingly simple. Now, if analytical solution is not possible, can we go for an approximate one? Well, even the search for an approximate solution using a polynomial that describes, for example, displacements, even that is not practical for the entire region. Now, FEM addresses this problem by dividing this plate into discrete elements and then attempts to find the approximate solution inside each element. Now, this first step for any FEM program then is that of discretization. There are infinite numbers of ways one can discretize this domain, but this is one way. We have divided this plate into a number of triangular elements. Now, this, taking just one example, this is an element, this one, and the points where these elements connect to the other elements, these are called nodes. Now, what is done is, instead of assuming a solution over the whole of this plate, which would be very complicated even if we were able to do it, we assume an expression of displacement for one element. Now, this step is called selection of approximating function. Now, this approximating function is valid for this whole element, for one element, as well as for all other elements. Now, this is also called interpolation function or the displacement function, because we start with displacements. If we are able to calculate those, then we can go on to strains and stresses. Now, a simple expression for displacement could be something like this is a linear expression. If this is x coordinate and this is the y coordinate, as you move along this element in the x and y directions, your displacement value, it changes linearly. Now, this is one example. Now, this leads to form of the algebraic equations for one element, and that, because we are talking about a generic element, then this form will remain the same for all other elements. Now, this is the second step. And the third step for any FEM program is calculation of all elemental equations. We do it for this one element and then you do it for the second one, third, fourth, and that is how you cover the whole domain. Now the fourth step is to assemble these elemental equations to obtain system equations. Here it must be noted that the forces or the boundary conditions, they can only be applied to the nodes. So for example, in this problem, this force F, it is a distributed force, but in FEM we can only apply the loads on the nodes. So in this case it will become F over 2. The next step is the application of boundary conditions. The boundary conditions again can only be applied on the nodes. So although this whole line is fixed, when it comes to applying the boundary conditions, we can only apply them on discrete points on the nodes. So for all these, we have u is equal to. Sixth step, we solve the resulting equations for displacement. Recall that this expression, and we have for 2D problem, we'll also have an expression for the y displacement. This expression is valid for each element, but this is a function of the nodal values. If we know the nodal values, we can then interpolate, and that is why it is called an interpolation function. But unless we know the nodal values, we cannot know the values at the inside, and nodal values to this point till point number 5, they are unknown. So now for the first time, solution of the resulting equations give us displacements, and the final step is the calculation of strains and stresses in this order. Now there are a few things to be said about this process. The first two steps, these are called pre-processing. The final, this is called post-processing. This could be von Mises stress or principal stresses or what have you. And the actual solution phase, which takes probably the most computational time, is this one. As far as this pre-processing is concerned, you just, once you make the equations, or you get the form of the equations, and then you store them in a library. The step 2 is just a matter of choosing that form from the library. One more point needs to be emphasized here, and that is, as a result of this type of loading, there will be very high gradients of stress here in this region around the corner. So even this element size, this can be very large for our purposes, because if we are going to select a relatively simple function, In this case, it is linear, but it could be quadratic, but it is still very simple. The gradients could be too high for that. So we may need to subdivide this region further, and we can do it easily in FEM. For example, we could divide this further like this. We are making smaller and smaller triangles. So in this way, we are able to make the mesh finer where there are higher gradients and rougher where there is no such thing. So this is the flexibility of FEM. Now number 2. Which starts with selection of an approximating function and ends with the form of the algebraic equation that fits that particular element. For that purpose, let's take up a simple 1D element that mimics this type of body. This is a bar with constant cross-sectional area A and a length L, and which is subjected to end forces only. There's no force in between. Now this sort of a body is mimicked accurately by this 1D element, and this is called one-dimensional linear bar element. Now by convention, this is the I node and this is the J node, and this is subjected to a force on the I node and a force on the J node. These are just symbolic. The direction could be to the right or to the left, and if because it's a 1D system, so there's only one coordinate, x coordinate here, and let's call this point the origin, the arbitrary point. Now at node I, the displacement is ui. At node j, the displacement is uj, and for constant cross-sectional area and the element subjected to only end forces, we can be very confident that distribution is linear. If this is ui, obviously ui is in this direction, ui is in the x direction, but if the magnitude is shown in vertically, then ui and uj, magnitude of uj, then they can only be a linear distribution. Now because this is the origin, we can further say that this is the location of xi lies node I, and at a distance from the origin xj lies node j, which means then that this xj minus xi is the length. Now because we know that in this case the distribution is linear, and we're talking about step 3 here. We're talking about step 2 here, selection of approximating function, which will lead to form of the algebraic equations. So let's write that down here. It has to be a linear function, because we need not go beyond linear. Linear will express it perfectly. Alpha 1 plus alpha 2. This is just an equation of a straight line. Now, this we are assuming, and in this case our assumption is spot on, that this expression holds on the whole body from I node to J node and everything in between. So if this is valid for the whole of the element, then it is also valid for node I and node J. Writing this for node I, we get alpha 1 plus alpha 2 xi, and writing this expression for J, node J, we get alpha 1 plus alpha 2 xj. Now, this is our displacement function or interpolation function. Now we have two equations with two unknowns, two coefficients, alpha 1, alpha 2. We can solve them simultaneously, and it can be shown that alpha 1 turns out to be ui xj minus uj xi over xj minus xi, which is ui xj minus uj xi over L, because xj minus xi is L basically. Now alpha 2, similarly, second coefficient, this is even simpler, uj minus ui over xj minus xi, which means that this is uj minus ui over L again. Xj minus xi is equal to length L. Now we have alpha 1 and alpha 2. Substituting them back in our displacement function, we get u is equal to, after a couple of steps of simplification, we get xj minus x over L ui plus x minus xi over L uj. Now we can write this down as ni nj ui uj, where ni is equal to xj minus x over L and nj is equal to x minus xi over L. The term interpolation function makes great sense if you see this expression. What it does is it gives you the value of u anywhere in the element. Of course, nodes I and node j. If you know the displacement at node I, which is ui, and node j, which is uj, and you know the shape functions, then anywhere in between you get this value of u. This matrix, this is called shape function matrix, and these ni and nj, these are called shape functions. So this shape function matrix, basically this transforms the nodal values of displacements to the general expression for u anywhere, which is valid anywhere in the element. Now this is the first step. Now we have to somehow go to the shape of the algebraic equations for this one element. We are just talking about one element yet. And the shape for that, for stress analysis problems, which are essentially equilibrium problems. We are going to use an approach called the principle of minimum potential energy. So in the context of this one element, as a result of forces being applied, displacements ui and uj, out of the infinite combinations of ui and uj, they will take the values which minimizes the potential energy of this element. Now, first of all, we need to write the expression for the potential energy. Later on, we'll minimize it. This is the potential energy, I, and this is the strain energy. This one is the work done by external forces. Now, work done by external forces is very easy. There's no complication there. Force Fi is applied at node I and Fj at node j, and the displacements are ui and uj. So the expression for W is very simple. W is equal to ui Fi plus uj Fj, which can be written in matrix form as ui uj Fi Fj, or symbolically as transpose, where u is the vector of nodal displacements and F is the vector of nodal forces. So much for W. As far as strain energy lambda is concerned, the general expression for strain energy is the dot product of the strain vector and the stress vector over the whole, integrated over the whole body. Now in this case, it's a 1D problem. There's only one non-zero value of sigma. So as far as we are concerned, we can write, for this problem, we can write this lambda as simply epsilon and sigma are simply numbers here, because there is just one non-zero component of stress in this case. Now, because we know that for 1D problems, we have this expression, we can get rid of sigma by substituting the value of sigma here, so we get rid of one variable. Now recall that in our case, the element or this rod has constant cross section area. So instead of volume integral, we can convert this into a length integral by writing this dv as a dx, and now it's a matter of integrating it not on the volume but on the length, because a is a constant. Now a and e are constants, they can be taken out, ae over 2, and we are left with this expression for strain energy. Now we need to substitute this epsilon. Now recall, we have just a few minutes ago derived this expression for U. In this case, epsilon is simply the 1D problem. Actually, this is the expression, but in this case, it's the same thing. We just have one variable. So we get minus 1 over L ui plus 1 over L uj, or in matrix form, we can write this as minus 1 over L 1 over L ui uj. Now, just as we named a matrix N matrix a few minutes ago, now this matrix, which links the nodal displacement values with the strain, this is called, by convention, this is called the B matrix. The N matrix links the nodal displacement values with the general expression for displacement, whereas the B matrix links the nodal displacement values with the strain value. Now, this B and N matrix will be with us for the remainder of this course. Moving on, we now know the value of epsilon, and we are in a position to put it here. So let's go on and do it. This becomes because these are matrices, epsilon value is a combination of two matrices, and we are going to have to use epsilon square, not epsilon. So by the rules of matrix operation, we will write this expression as this is the B transpose, because B transpose B is the B matrix. So this is the B transpose, and now comes the B itself. Now this becomes all these U's 1 over L, all these quantities, they are basically constants. So we can take these out and we can write it like all these go outside, and we are left with this integral. Simply, now this integral simply becomes this, simply becomes x, and we have to take the limits, and this becomes xj minus xi, which is nothing but L. So we have this L here. So let's simplify, and this L, AEL over 2 UI UJ, and let's multiply these two, and we get 1 over L square minus 1 over L square minus 1 over L square and 1 over L square, and here we get UI and UJ. Now these L's in the denominator, we have L squares. So if you take them out, we are left with This is the expression for strain energy. And symbolically, you can write this as simply where U is Ui Uj and K, which is called the stiffness matrix. This is AE over L 1 minus 1 minus 1. It's called the stiffness matrix, and this again will be our friend till the end of this course. Now we have the expressions for lambda as well as the expression for W, so we can write the expression for potential energy, which was nothing but this, and let's write it down. Now this is the expression for the total potential energy. Now for the system to come to an equilibrium, the potential energy needs to be minimized. This means that we need to differentiate it with respect to the degrees of freedom. In this case, there are 2 degrees of freedom. So we have to differentiate it with respect to both degrees of freedom. Or in other words, or we can write the same thing as this, and we have to put it equal to 0. That will give us the minimum value. Now, simple matrix algebra will tell us, and the same result we will get if we do the calculation in expanded form. For example, in place of U, you write Ui and Uj. In place of K, you put in the actual values. So if you write it in the expanded form, you'll get the same result. Using the matrix algebra, we can simply say that this is equal to this, and we differentiate it with respect to U, we are left with simply and this is equal to 0. So our expression for one element is this. This is an algebraic equation where K is A over L 1 minus 1 minus 1 1. U is equal to Ui and Uj, and F is equal to Fi and Fj. This is for one element. This is the general shape of, and this is called the elemental stiffness matrix. And for this, let's put an E here to tell you. So this is the shape we were talking about. Starting from displacement function, this is the shape of the elemental stiffness matrix. This is the shape of the elemental displacement vector, and this is the shape of the elemental force vector, and these combine in this form. Incidentally, this form will always be the same for equilibrium problem. Ku is equal to 1, whether it's a beam problem or a bar problem or a 2D problem or whatever. This expression Ku is equal to F, this will be the same, although these shapes of this K matrix, these will of course they'll be different for different problems. Now this is for one element. What to do when there are more than one element? Obviously, the next step, once we have this, we make use of this expression to calculate these equations for all the elements separately, and then we have to combine them together. So what happens is this for the whole system. The expression for W takes the form of U1 F1 plus U2 F2 plus until we get U and Fn, the last force. Similarly, the expression for potential energy will take the form from one element to the total number of elements. E, let's call it for E elements. E is the total number of elements in the system. Strain energy for each element. In this case, there was just one element, but we have to calculate strain energy for all the elements and then combine them together. And the last step, that is the minimization of potential energy step. This will, in this case, yield the same form, but in this case, there will be a summation of K's for all the elements in the system, followed by the usual, this is equal to 0, which will give you a similar expression, but this expression is for the whole system, not for one element. So in this case, this was element displacement vector. This case, element force vector. Now we have the same shape, but this one is system displacement vector, system force vector, and this summation, how to sum this up? This is affected by something called connectivity table. This is very simple. We will illustrate this by an example.